All right, I'll start over. As a review of the topics we've covered so far, we've been doing logic so far and truth tables. And here's our tables for connectives, and these are from the notes that are posted on the website. So we have our truth table for OR, which we remember has 3 ones, and has just one when P and Q are both true. Not negates the proposition that it's in front of. P implies Q. What was the homework assignment I gave you on P implies Q to prove to yourself? Is anyone? So you were supposed to look and see, was P less than Q? Is that the same function? So let's look. Okay, so let's fill out the truth table for P less than Q. In the first case, P is 0 and Q is 0, so let's put an equal on there. P less than or equal to. Okay? So if 0 is less than or equal to 0, that'll be true. And the second one, in the second row, we have P is 0, Q is 1, P is less than or equal to Q is true. And in the third case, we have P is 1, Q is 0, so P less than or equal to Q is false. And in the fourth case, 1 is less than or equal to 1 is true. So implication is just like a logical less than or equal to function. So that's another way to remember what happens when you do implication. So now that really tells you why order matters with implication, because in less than or equal to, it really matters which number you write first, right? So in this case, this is another good way to remember implication. We had 2 other functions that we looked at. One was P is equivalent to Q, and this one was true when both P and Q had the same value. So when P is 0 and Q is 0, this function is true, and when P is 1 and Q is 1, this function is true. The last function we looked at was exclusive OR, and that one was true only if they had different values, if P and Q have different values. Are there questions about those functions? Okay, so we've done some formal proofs in class, and those use logic rules. So let's do an example of, I promised you an example of a longer truth table proof with several variables, so let's work on that first. So let's give you an example. Let's prove. We're going to prove P or Q implies S, logically implies P implies S. So we're going to prove this. If we prove it by truth table, we need how many rows in our truth table?
8.
We need 8 because we have 3 inputs with 2 values each. So remember when I made a truth table for 2 variables, I put 2 zeros for P and then 2 ones if that was the first column. So now that I'm going to have 8, I'll put 4 zeros for P. And my Q will look just like my old first column twice. And S will alternate 0, 1, 0, 1, 0, 1, 0, 1. And again, this is binary counting. Since we have 8 rows, this counts from 0 to 7. At the top of the truth table, I write what I'm proving, and then I'm going to make a column under each item. So which column in this truth table is my result column? The logical implication column with the double arrow. So the double line arrow, this is my result. So this is the last thing I'm going to fill out. I can fill out all the other ones in any order that I want to. So I'll fill out S because I'm just copying it over. Now I'm going to fill out P or Q because this implication, the first implication here, comes from these 2 values. So I need to fill these out before I can fill out this implication. So our logical implication is going to compare columns 1 and 2. So P or Q, we have to look at each value. The OR is false in the first case and in the second case. True in the next 2, probably true for the very rest. of the truth table, and it is. And then we'll check the implication value for P or Q implies S. So when we have a 0, implication is always true if the hypothesis of the implication is true. If we have 1 implies 0, that's going to be false, and 1 implies a 1 is true. In the next row, we have 1 implies a 0, that's going to be false. True, 1 implies 1, 1 implies 0 is false. Remember that we can think about less than or equal to when we're doing implication. So I'm comparing the left and the right. 1 is not less than or equal to 0, so I put a 0 in the truth table. Our last case is 1 implies 1, or 1 is less than or equal to 1. Now we need to fill out P implies S. So in the first 4 rows, we have that P is false. So this implication is going to be true because our hypothesis is false. So the implication is therefore true in all of those cases. And then in the last 4, it's going to be true only when S is true because P is true in the last 4. So this implication is only going to be true when S is true. So it's going to be 0, 1, 0, 1 for the rest of that. Now what's our goal when I do a truth table proof?
They all line up.
Our goal is to have all 1s in the logical implication column. In other words, the 2 columns that I'm comparing, I should have either be the same or I should never have 1 implies a 0. Right? So I could have 1 implies 1 is true. In the second row, I have 1 implies 1. 0 implies 1 is all right. 1 implies 1 is true. 0 implies 0 is true. 1 implies 1 is true. 0 implies 0 is true. And 1 implies 1 is true. That's when you sigh with relief because you did your truth table proof correctly. You can imagine that as you add variables, you'd be less and less happy about doing truth table proofs, right? So you can also prove this with a formal proof. Are there any questions about this one before I try a formal proof? Okay, and I need your help with this because, after you've been doing this for a while, you forget. And besides, it's good for you all to work the problem. So what do I write first when I do a formal proof? Givens. I write my givens. So my givens is just this, right? Because since I'm doing a formal proof, my givens is the items on the left of my logical implication, and what I'm proving is on the right. So I'm proving this, and this is given. So I write that in my formal proof. And my reason is given. When you do any proof of any kind, the goal is that someone else can read it and believe you when you say that you got from the given and did legal steps to get to what you were proving. So anytime, actually, when you're doing any homework in any science or mathematics class, you should always list things in a way that someone can read it and believe that you didn't do any magical steps in between. Okay? So when you're doing your homework, think about that. Think about someone reading your homework and thinking, does this make any sense? Can you get from point A to point B? Or line 1 to line 2? So that's the whole idea behind a proof, is that we're making a list so someone else can read it and verify that what we did makes sense. So we're going to do a trick here. Do you remember that? Let me just write what my little trick is. We're going to do this proof without the trick too, just to see how to do it. But this is a trick. Why can I write this line in my proof? If I write P implies P or Q, why can I write that? Is it something that's always true?
Yeah.
Yeah, if P is 1.
If P is true, then P or Q is going to be true no matter what Q is. And this rule is called the addition rule, which on your list of rules that I've given you is the very last one. It's rule 32.
Excuse me, is that the P and Q or P or Q?
It's or. It's very important that I use it or because P does not imply P or Q. P and Q.
Okay.
Sorry. It does imply P or Q. I can OR anything to something that's true, and I'll still get something that's true. So if I tell you I have $1 in my book bag, that's true. And I say I either have $1 in my book bag or $1 million in my book bag, that's still a true statement because I do have $1 in my book bag. I can tell you which part is false. But you can OR anything to this true statement and still remain true. So why did I add that to my proof?
Get it in the right order so you can say later on P goes to S.
I did it exactly so I could say that P implies S, because if I combine lines 1 and 2, then I get P implies S. So that was from lines 1 and 2 and the rule called hypothetical syllogism. And this is your favorite rule. And if it's not your favorite rule, it will become your favorite rule. Now this was a nice quick way to get rid of this OR Q that I didn't want. If I wanted to do this proof another way, let's just start with line 2 again. And let's assume that I didn't remember that I could do the addition rule. What would you try doing? We know that we want to get rid of the Q somehow. So what might we try doing? Any ideas? I only have line 1 as my only given. I would need to change the implication into something else probably. So let's change it into an OR. How do I change an implication into an OR? I negate the first variable and OR it with the second one. So I'm going to negate this statement and OR it with this one. So I'll put not the quantity P or Q and OR that with S. And that's using my implication rule on line 1. Now I need to use De Morgan's in order to see what that not really does to this statement. So De Morgan's on not the quantity P or Q gives me
Not P and not Q.
not P and not Q. And that gets ORed with S, so that was from line 2. And De Morgan's so now I'm hoping to get that Q somewhere far away from the P. And I'd like the S to get closer. So I need to do distribution on this. So I need to figure out how to distribute it so that I have the P and the S together and the Q and the S together. And then somehow I can get rid of the Q and S, hopefully. Okay? So if I do distribution on this, this is just like, the distribution rule is just like doing multiplication and addition in regular math, except that in logic, the order of operations of and or is equal. So in regular math, order of operations of and or is multiply and plus, and you do multiply first always. In logic, there is no order of operations for and or, so you actually have to give a rule for doing those. So the distribution rule, if I have, say, A plus B times C, in regular math is going to give me what?
AC plus BC.
AC plus BC. And that's how the distribution rule works, no matter whether you have an or an or wherever it is. So what it is I'll take the first variable and that operator along with the last variable, and then use this operator, and then take the last variable, the second variable with the last one, with that second operator. So we'll do that. So I'm going to take not P or S, and that gets ANDed with what? Not Q or S. So that distribution rule is written on your axiom list, both of the rules, depending on whether the AND or the OR is on the outside. So this is line 3, and distribution. Now on line 5, I knew that I wanted to get rid of the Q. Any Q's that appeared in there, I would like to get rid of them. So if I know that line 4 is true, I have two things ANDed together. And remember that a proof is a list of things that are true, that are all ANDed together. So I could just write one of them on the next line. Right? If I know P and Q is true, I know that what? I know P is Q, true, and Q is true. So using that rule, I have two items ANDed together here, so I can simplify to get just one of them. But that's very important that it's an AND operator. Because if it were an OR, I wouldn't know which one was true. Right?
Yes.
But since it's an AND, I know that both of them are true, so I can simplify and say, if both of them are true, then one of them must be true. And that's from line 4 and the simplification rule. And now what will my last step be?
Reverse the
Implication.
implication.
I'll use the implication rule the other way to change an OR back into an implication. So from not P or S, I get P implies S. And that was from line 5 using the implication rule. So which proof is better? The top one or the bottom one?
Top one.
That's a trick question.
Yeah.
Someone once asked Abraham Lincoln how long should a man's legs be? And everyone knows he was very tall, right? And he said, long enough to reach the ground. So if you ask me, how long should my proof be? I'll tell you long enough to get to what you wanted to prove. So neither one of these is any better than the other. Yes?
Yeah, the first proof. Will you go back to the number 2? I didn't get it clearly. The addition rule.
The addition rule is listed on your logic axiom list.
So we just pick it.
And it's written as P implies P or Q.
Yeah.
That's the entire, this is the rule in its entirety. The entire rule is written on this line, because in a proof, I can write anything that's true, I can put it into my proof.
Yeah,
So if I wanted to, I could write Tiffany has red hair in my proof. It just doesn't help me.
Yeah, but how, from the one given, how did you decide to use the addition rule? That's the part I don't get.
Well, I knew that my favorite rule is hypothetical syllogism, and it helps me get rid of variables that I don't want to see in a proof.
Okay.
And I knew that I didn't want this Q.
Okay.
And actually, I would really just like to replace this whole thing with P.
Okay.
And so what I really thought to myself was I'd really like for P to imply whatever this is,
Oh, got you.
and then I could use hypothetical syllogism to get rid of this variable.
Got you.
And that's exactly what I did. So writing this down, I just had to verify that it really was true. P implies P or Q is always true. Because if P is true, then P or Q is always going to be true. So that's something that you can write in a proof. Anytime you can write one of the rules into your proof if it helps you get where you want to go. Now I did say that I'm going to answer your question, how long should a proof be? I'll say long enough to get to the end, but I'd also like for you not to write a lot of things that aren't useful. So in this case, in this proof, every single step I did was motivated. And that's what I'd like to see in your homeworks, is that every step that you do has a reason. The reason why I did this is I didn't have much choice. Okay? But I did know that I would like to get rid of the Q. And the only way to do it was to somehow get to an AND where I could do simplification. And I knew I was only going to get to an AND if I changed this into an OR and then redistribute it. So that's the reasoning behind that. Because I knew I needed to get rid of the Q, and so I was going to have to use simplification to get rid of it because I had no other lines to combine with it. So I had to use the implication rule to change this to an OR, and then De Morgan's and simplification to get to what I was trying to prove. So that, for me, comes really naturally because I've been doing this a long time. And it will start to come naturally to you. The more proofs you do, the quicker you'll see what the very next step is to do. So it's not bad to write things that aren't useful, especially when you get started, but I want you to be thinking about what would you like to see next in your proof and try to work towards that instead of just writing anything that you know is true. Okay, are there questions about this? I'd like to ask you, would you like to do some more formal proofs, like working together to figure out how to do one, or would you like to move on to the logic and circuits? We will move on to those, but I can do some more formal proofs if you would like, or we can go on to logic and circuits.
Let's go more.
Are you saying if we don't continue on, then we get out early?
No, you'll be here
Or,
the same amount of time.
not that I want to get out early. I mean, so you're saying we're going to spend more time on circuits versus do more formal proofs?
So let me give you an example problem, and I'd like for you to work with your neighbor, if you could, on this problem to figure out how to prove it. And the problem is this. Given S or G implies P, and you're also given P implies A, prove that not A implies not G. So when you work with another person, I would like you to have one person write things down, and the other person might have the rule sheet, but I don't want you to look at the axiom list just to think of all the true things you could write down. Okay? So I want you to look at what you're trying to prove and see what you'd like to do because of that. So with your neighbor, yes. Do we have some more of those?
No, I hadn't.
You should be able to share with your neighbor because we're doing a group problem. So you can come have a seat next to someone. Do you all have one? Already got two here. So try to use your neighbors. I don't have any extras.
If we get to not P, not P and not so if you can get not P here
So we want to get rid
and
of
not,
F.
That's right.
The P.
then we can just.
So in this problem, let's just try to be like high level on this problem. We know we want to get the A and the G somehow together. So we know we want to get rid of that S and the P. So the only way to get rid of the P, though, is to combine lines 1 and 2, right? So if we label that lines 1 and 2, then I can combine them using what rule? Hypothetical syllogism, which is on your sheet. Very first one, because it's your favorite. Okay? So you'll be able to combine those to get rid of the P.
So S and G, or S or G implies A.
Mm-hmm. Right, now we would really like to get rid of the S, right? And we might need to do a trick like we did in that last proof.
So G implies S or G.
Well, we want to get rid of the S. That's our main goal, is to get rid of the S, right?
Yeah.
So what was the trick we did in not the last proof, but the one before that?
So
We did the addition rule, which was to say that S implies S or G. So if we look at line 32,
but that would leave us with the S, wouldn't it?
no.
Okay.
Well, I write that because I want to use hypothetical syllogism with that. With these two, I'll be able to get rid, I'm sorry, G implies S or G. You're smart. You're very smart. G implies S or G, right? That's the addition rule, right?
Okay. Yeah.
So then you'll be able to combine those and get it. So, right. How's it going over here? Terrible? Okay, did you write your givens? Okay, you'll be doing better after you get started.
Okay. Okay. Yes, that's addition.
Okay, you did G implies G or S. That was your addition rule. And you did that because you wanted to get rid of the S.
Yes, yeah.
Very nice.
P.
G implies P, right.
Implies P.
Go ahead.
Check from number.
So, and you also need to write down this one because this is another given. So you can put that as line 4. Okay? And you're well on your way. So how's this going over here? Okay? So we were trying here to what?
Well, using this other way, we had gotten to, is using these 3 steps, we had gotten to G implies S or G.
Mm-hmm. That would work.
And then using addition, we got to G implies A.
Line 4 is P implies A.
Yeah, that's just how you
Okay, you didn't write that stuff down, so if you write that stuff down, you'll be far along, very far along. All right, that's a good one. That's a good way to do it. Okay, how's it going?
I'm not so sure.
Because
P implies A.
3 and 4.
That means not A.
That's very true.
Also, because S or G means P, means not P means not S and S or G.
Right.
So if you distribute, I think to the change form into N, right? So I'm not so sure if this means not P means not G, not
This is going to be using the simplification rule. Let me see if I have something for that. Implication. Yeah, so you'll be able to use this. You need to use the simplification rule. So simplification is here. If I have an and, this is an and, that implies that one of them is true, right? So this implies that not G is true, and then you'll be able to combine. So you need to write not S and not G implies not G.
So
that implies
this
not G, right?
This implies not G.
These two, this implies this automatically, right?
Right.
And so therefore this implies this,
Okay.
right?
All right. Okay. So
And then you'll get not A implies not G if you do hypothetical syllogism again. So
okay. So this one really can means both, not G or not S.
it does, right?
All right. Thanks.
Okay, let's work together again. Okay, so first we have to write down our givens, right? That's always what we do in a proof. So our first line should be S or G implies P, and our second will be P implies A, and both of those are given. Now, it's very important for you to write down the rules and the line numbers. So you can do some side work if you like that doesn't tell you what rule you used or what line number or even look remotely like this. But in the end, you want to work this way. So I recommend always writing the statements and the reasons every single step, because then you won't have to go back and double check yourself. So we knew that we wanted to get A and G together on the line. And there are several different approaches to doing this. The first thing I could do is look for a line that has A or G in it. So line 1 has G and line 2 has A. So I need to get those together, but I need to get rid of the S and the P also. So if I combine lines 1 and 2, I can get rid of P. So I can use our favorite rule, which is hypothetical syllogism, to combine the first 2 lines to give me S or G implies A. And that was from lines 1 and 2 in hypothetical syllogism. Now I've already used lines 1 and 2, and I still have to get rid of an S. So I could use, again, we did a trick before where we used addition, when we had an or, where we'd really like to have just one of the single variables. And we really like the G, right? So let's write that if we know G is true, if we know G is true, then we know what? S or G can be true. And that's using the addition rule, just writing it straight into our proof. And then I can combine 3 and 4 to get G implies, I keep writing Q's, G implies A from lines 3 and 4, and hypothetical syllogism again. And then on line 6, I look back at what I'm trying to prove, which says not A implies not G. So I need to reverse the order of my implication, which I can do by what rule? The contrapositive rule tells me that if it didn't rain, I must not have gotten wet. So here, raining is G, getting wet is A. So not getting wet means it didn't rain. So that was line 5 and contrapositive. So just to show you that there are many, many different ways to do a proof, let's do another solution to the same problem.
Wait, what about there? Next week.
And I'd like to hear from you all, because I'm sure that some of you did your problem differently than I did or didn't use the addition rule. So what was something that someone did first for this problem? If we're proving not A implies not G. Everyone did exactly what I put up. I'm amazed. Yes.
We did not, and then S or G.
Actually, we did hypersyllogism first.
Oh, we did hypothetical syllogism first.
On lines 1 and 2? Okay, so again, we did hypothetical syllogism because we knew that could get rid of the P for us. So we got S or G implies A, combining 1 and 2 with hypothetical syllogism. And then you did contrapositive next?
No, we did
No.
implication.
You did the implication rule because you saw that you had a not G and you thought you'd like to get that out in the open there. Okay, so if we use the implication rule, we negate the first variable and OR that with the second. So that rule was from line 3 and the implication rule. So then we must have done De Morgan's from there. So that would give us not S and not G, ORed with A from line 4 and De Morgan's.
I think we simplified the left side.
You use simplification on the left side. Okay. There's a little problem with that.
Okay.
And that is I have S and not G ORed with something else. So I can't simplify part of a statement. It's kind of like you know that it's true, you feel in your gut that it's true, but the rule doesn't tell you that you can do it since it's ORed with something else.
Okay.
So what we need to do instead is we can either use distribution here or we could have used simplification up here. We could have said S implies, G implies G or S and then combine them just like I did in the last one. So that was a very good point because we have a logical implication. We can't use logical implications on parts of lines. So if you look at your axiom list, you have 2 sections. The top section is logical implications. And that includes hypothetical syllogism, the disjunctive syllogism, modus ponens, modus tollens, absurdity, simplification, and the constructive dilemmas. Those you can only use on whole lines. So if the left-hand side has to be on a line, and then I can conclude the right-hand side. So I have to know that that part is true. So since I'm not sure that this is true, because this might be true or this might be true.
Oh, okay.
So I'm not sure that this is true, so I can't conclude the right-hand side of that. Although it does end up being true, you can't do that. Okay, so we need to do distribution here. So that will give us not S or A ANDed with not G or A. So when you do distribution, just think about the outside variable and operator gets paired with each of the inside ones. And the inside operator is now the main one. Okay? So then, we know we want this one because we don't want the one with the S in it. We want the part of this that has the G and the A. So we'll do simplification on the next line. But before we do that, that was from line 5 in distribution. And by the way, on your homeworks, it's all right if you abbreviate the rules. I know them, the TA knows them, you know them, so we don't need to write all the letters as long as you write enough to know which rule we're using. Okay, so we're going to do what on the next line? We'll simplify because we have an AND on line 6, and we can use simplification on that, so we get not G or A. Did I do that right? I sure hope so. 6 and simplification. In line 8, I'm going to get G implies A if I do implication rule on line 7. And then if I do contrapositive, I'll get not A implies not G, and that's what I wanted to prove. And that's the contrapositive rule. So what's another way we could do this proof? We did direct proofs so far, right? So last time we learned that we have also another method which is called proof by
Negation.
contradiction. So we could do a truth table proof, that's true. And in your packet that's on the web that you can print out, this is done by truth table and by short formal proof also. So let's do this one more way by proof by contradiction. Sometimes proof by contradiction is a lot more simple because sometimes you don't see the way to get to what you're trying to prove. So the very first thing after we write our givens in a proof by contradiction is to write what we're proving. We put a not, and then we write what we're proving. And that's called negation of conclusion. I have a question for everyone. Can I use negation anytime I want to in a proof?
Negation.
Just negation. Anytime I want to.
You can use double negation.
I mean, I'm asking you because I get homework papers sometimes that say they have a line, and then the very next line is the opposite of that, and the reason given is negation.
If it's useful, but and if you distribute it correctly, depending on what you're looking at.
If the first is true, then the negation of that, wouldn't that be false?
Right. That's very good. Okay, so in this proof, I better not write not the quantity P implies A, because in this proof, P implies A is true, so the opposite of that will be false. And that means if I write the negation of something in my proof, of something that's already true, then I'm putting a false in my proof, and then everything after that is now null and void. Okay, so that messes up your proof if you negate something that you have in there. This is a special case. The only time we get to negate anything is when we negate the conclusion and put it into our proof. And that's because we're going to try to get a contradiction. And we can't write any other false things in there, or else the contradiction could come from something else that was false. So the only time we get to put something false in is if it's the conclusion, because we want to put that in to prove that the reverse of it is true. So that's the only time I want to see a negation next to any statement that you have, is if it's the negation of the conclusion. And you can put double negation. That's the only negation that you get to put on the reason side. Okay, so in order to change this implication into something else, because remember in our proof by contradiction we wanted to negate it and simplify it. So we want to use De Morgan's if we can and simplify, because that gives us our money to combine with our givens to find a contradiction. So let's do that here. I have to change my implication into an or before I can do De Morgan's. So I negate the first variable, and that gives me not A. I'm going to skip a step and put A, change the implication into an or, and copy the second variable. So that was from line 3 and the implication rule.
Thank you.
Penalize that if we skip a statement like you've done, will we be penalized?
No.
Do we reference the fact that we did double negation and the reasons?
Yeah, actually, that's good to do. So then you'll remember that you also did double negation at the same time. Okay. Because on your proof tutorial, which is going to be available later this week, I'll send you an email when that program's available. You will. It's not going to let you skip double negation, or it'll tell you it's okay, but you skipped double negation. Okay. So now I need to do what rule?
Distribution.
I need to do De Morgan's, which is distribution of not. So I'm going to have not A, and then the or changes to and not G is really not G, so I won't skip a step there. That's 4 in De Morgan's, and I would have to do a double negation step there, not A and G, from line 5, and double negation. And we have an and, so we can simplify.
Yeah.
So we use simplification to get not A on a line by itself, and also to get G on a line by itself. So from line 6 in the simplification rule, we got both of those. Now remember that our givens were our store that we're going to use our money. So our money is the stuff we get after we finally get to do De Morgan's and simplification. So here's our little store, and we have some money to spend at the store. And we want to buy 0. Okay?
Excuse me, when do you decide 7 and 8 are your money?
I decide that they're my money. I mean, everything after the negation and conclusion, all that stuff is my money. But I decide that it's my money when I'm done doing De Morgan's and simplification. When I can't do any more of that, then I know I can go up to the store with my pieces.
Right.
Okay? So we have a decided rule on proof by contradiction. We know what we're doing. We write the negation and conclusion. We try to do De Morgan's, and then we do simplification. And then we have our money. We go to the store. Okay? So our first piece of money is not A. So what can we buy with not A? Well, where do I have some A's in my givens?
Number 2.
Line 2. So if I didn't get wet, then what must have not happened?
It must not
It
have.
must not have rained. So if P is raining and A is getting wet, I know I didn't get wet, so it didn't rain. So I know not P. And that was from line 2 and from line 7. And the rule is called Modus Tollens. So we've sort of used this money, and this is new money. Okay? And let's go ahead and use not P. So not P with our givens gives us? Doesn't work with this. It only works with this, right? So it gives me not the quantity S or G using the very same rule again. So combining lines 1 and 9 and Modus Tollens. And I apologize for these Latin names, but that's what they're called. Modus Tollens means that if you know the opposite of the conclusion of an implication, then you know the opposite of the hypothesis. In other words, if you didn't get wet, it didn't rain. That's Modus Tollens. Okay, so now 11, again, anytime you get something in a proof by contradiction, you want to do De Morgan's and simplification if it has a not on the outside. Okay, so let's do that with this. We get not S and not G with line 10 and De Morgan's. Because a not on the outside of anything, we can't use any of our rules if there's a not on the outside of something, right? Because all of our rules assume something's true and derive something from that. But if you have a not outside of it, then the thing on the inside is not true at all. So I want to distribute the not so I can use my rules. So 8 and 11 are going to finally give us what we want, but we want to do simplification first. So we'll do 11 and simplify to get not G. So that was the same process we used with our negation of the conclusion, was to do De Morgan's and simplification when we saw a not. And then when we see two things that are opposite, so again, this was money right here. So we saw on line 8, we saw G, and on 12, we saw not G. So those are opposites, so we put them together just to verify to the reader that we do have two opposites. 8 and 12, and conjunction is the rule that tells me that I can take two things in my proof and put them together on the same line with an and. And 14 is to write 0, and that's from line 13 and the definition of contradiction. So contradiction is anything anded with its opposite. And a proof by contradiction should always have the very last line should say 0, the previous line number, and the rule name is contradiction, and the line before that should always have a variable anded with its opposite, and the reason should always be conjunction, and then the stuff in the middle is what you have to figure out. So you know you have givens and the negation of the conclusion, then you've got reducing things to your money, right, and then buying things, and then at the end you should have conjunction and contradiction. Questions?
somewhere that we can go to practice doing these where we can have the answers, that's not necessarily the homework?
I have examples in your handout packet, and the very second pack of handouts, which will be ready next week, has example proofs with solutions that will help you study for the test. So, and also the proof tutorial that you'll be doing later, the program that you'll be doing, also has lots of examples, and it won't let you put in lines that are false. So it'll let you do the proofs. It doesn't tell you the answer, but it'll verify whether the rule you gave was the right rule and the line numbers are correct. It's a really cool program. Okay, let's do another proof by contradiction, and then we'll start with logic. Okay, we'll do one more. So if we know P or Q, and Q implies S, and P implies R, and I want to prove S or R, these are going to be my givens, so I'm going to go ahead and write them as if they're in my proof. If I do proof by contradiction, the very first step is negation of the conclusion. So I put a not, parentheses, and write my conclusion. And the reason is negation of conclusion. Okay, so I would like you to work this in pairs together and remind each other what the steps are. Okay, pairs or triples is fine. And I'll come around and see how everybody is doing. So what's the very first step you need to do? You want to use De Morgan's first and then simplification if you can. Right, so De Morgan's gives you the opposite of each of the variables and changes the or into an and. Right? It will be not S. So the or changes into an and. So I do it step by step. I just look at this and I write not S, and then I put and under the or, and then I put not R under the R. And then since I have an and, I can do simplification. So I can get not S on the line by itself, and I can get not R on the line by itself. That's good. And then I label those as my money. That's not technically required, but it helps you remember what you're going to do, right? Then you go back up to your givens, which is your store, and spend some money. So 6 and 7 are your money. Right.
It didn't rain, so we've got Q.
Right. So make sure that he understands all the steps you're doing, okay? Okay, how's it going over here?
Got to not S and not R.
You've got to not S and not R. That's excellent. So now what do we do with our money? That's our money.
We'll go spend it.
We need to go spend it. I know we're all good at spending money. We just got done with Christmas, right?
Okay, so it's going to, at least R is going to involve 3 and S is going to involve 2.
Right, so let's do one at a time.
Okay, so we'll do 8 with this 2S.
Right? If I have not S, then I get.
Then you can not Q.
Right, because if I didn't get wet, it must not have rained.
Right, exactly. And
Right.
that was
Write your line numbers.
2
and 6, right? And that was Modus Tollens was the rule name. So you guys are well on your way. So you still have some money left.
Right, we're going to do the same with R. So we
Okay.
can say 7 and 8. So we can say not R is not P for the same rate.
Right, very good.
3 and
You're doing great.
7 and
So you use simplification from this line, right? Right, good. Good. Right, so now this is some new money, so I can go back up to my givens and use it.
Yes.
Okay? So it's good to label your money. This is money here, right? And you got this from this, but you still can also get not S from this, and you're probably going to need to, right? So, but this is some money that you can also use up here. Okay?
So line 6 is
How's it
not S,
going?
line 7 is not R. Simplification.
From here, not
Yes.
as, not as, not R.
And what was the reason for that rule? Reason for that statement? That was the De Morgan's rule. Here's De Morgan's, right? If I have the not of a,
7
But you see number 1.
right? If I have the not of an or, that gives me an and. That's De Morgan. So you need to start getting used to writing the rule names. Okay? That's good, but this is correct. And then from not S, you got not Q. That's correct.
we have our money.
Right.
Same thing, because from here we get not R, because not R, we can,
Right. That'll give you not P, right?
yeah, not P,
Right.
that's right.
Okay, so we can do
Very nice. This and this are actually opposites.
Right. We're just trying to figure out how to write it. So,
Well, this one you can use De Morgan's the opposite way, right? That's not the quantity P or Q, right? Okay, you didn't write down the step he did, and that is to put not P and not Q using conjunction. So you'll need to get rid of these brackets because then you're going to get not the quantity P or Q. Got to be a little careful. So let's just use conjunction. Yeah. So put not P and then conjunction. And that's going to be, this next line will be not the quantity P or Q. Right, there you go. Right. No, you can combine that with line 1. Now you can do conjunction, and you have a contradiction, right? Because they're opposites.
Conjunction, compound.
Okay, so let's bring this back together. It looks like everybody was making some progress. So it looks like everyone did a good job of using De Morgan's at first. So we used De Morgan's on line 4 to get not S and not R. So that was line 4 and De Morgan's. And since that's an and, I can do simplification. So on line 6, I'm going to get not S, and on line 7, I'll get not R. And I'll go ahead and label these as my money, so when I'm working later, I can look at them and see where they are. Both of these are from line 5 and simplification. And I'm going to do this like one of the groups in class did, just to show you that we don't have to have like P and not P. We can have a quantity and its opposite negated, and we can still get a contradiction. Okay? So from this I know, from not S, I know what? From my givens, I know not Q. That was using Modus Tollens. From lines 2 and 6, Modus Tollens. Okay? And then we also knew not R, and we used that with line 3 and got not P using the very same rule. And that was from 3 and 7. 3 and 7, yes, gives me not P. And then if I wanted to put these together, this is what one of the groups in the class did. They put not P and not Q from lines 8 and 9 in conjunction because they saw P or Q was together up here. So they got the P and the Q together down here. Okay? And then they used De Morgan's backwards. So going from the and, they went to an or. So this would be not the quantity what?
Not P or Q.
Not the quantity P or Q. So that was from line 10 in the De Morgan's rule. And then we saw that we had P or Q on line 1. This is the exact opposite of it, so we'll do conjunction to put those two together. Sorry for writing small. So that was from line 11 in conjunction. 11 and 1 also for conjunction. And as we always have on a proof by contradiction, we'll put 0, and that was from line 12 and the contradiction rule. Because if I have anything ended with the opposite, it's a contradiction.
Yeah.
So there's more than one way to do a proof. So whatever you see first is fine. Because at this point, when we had not Q and not P, I could have immediately used the not Q with line 1 to get what? To get P. Because if this says I have an apple or an orange, that says I don't have an orange. So I must have an apple. And this P I could have gotten, again, from 3 and 7. And then I would have P and not P. That's another way to do the proof.
What's the name of that rule?
The apple-orange, that's disjunctive syllogism, which I believe is the second axiom. Yeah, it's the second axiom on your page. Those numbers on the axiom list that's on your handout are not very important, except that you will use them on the tutorial also. So it'll be good to have that sheet handy with you so you'll know the rule numbers for everything. But
Is it on the website?
the tutorial's not quite ready yet, so we'll be.
I mean, the sheet.
The axiom list is on the website. I posted it about 5 o'clock today, so you should be able to get it. Other questions about this problem? Okay, good. All right, the next important section of the class is logic and circuits. So we've been doing logic and proofs. And the next thing we're going to do is circuits. And again, we're going to be dealing with ands and ors, but we're going to be combining them to create functions instead of combining them to say when something's true and when something isn't, when one thing implies another. So we're not going to deal with implications that much when we do logic circuits. The first thing we need to do is know what gates are. Okay? So a gate, well, let me write down logic circuits. So in general, a gate is a logic device that has inputs and outputs. And in general, the output depends on the input. In general. It might not. You might have, for example, I think of the standard sort of gate or function. A gate also is just like a function. You have inputs and you get an output. I like to think of that like the post office. And you'd like to think that the mail that you put in there is the mail that goes out somewhere. They could also just have whatever letters they want and just send them anywhere they want to, not depending at all on what anybody gives them, right? So a gate could have outputs that are independent of the inputs, but in general, useful ones depend on the inputs. Okay, so our most important gates are going to be for our most important operators, which are and or. Remember that we could derive any logic function from ands and ors. Any of the ones that we've been talking about, we said we could derive any function from ands and ors, and we can. So that's why they're the most important gates. So the AND gate looks like this. It looks like a big D. And it's standard for the inputs to be on the left and for the outputs to be on the right. So our inputs are going to go into the straight part of the D, and our outputs will come from the round part. So if P and Q are inputs to this AND gate, then our output's going to be P and Q. So this is a piece of hardware that will implement our truth table. Okay, so let's make that a little more concrete. So if I have an AND gate and I put 2 zeros in, what's the output going to be?
0.
0. If I have an AND gate and I put 2 ones in, what's the output going to be?
1.
If I put 0, 1, what's the output going to be?
0.
0. And if I put 1, 0, what's the output? 0. So this gate will give us exactly the function that we list in the truth table. It will only give us a 1 in the output if we have a 1 in both of the inputs. And the OR gate looks really similar. Depending on the software or the person drawing it, you might get confused, but try to make the back curved. And sometimes you'll see this pointed just to make it double, but also it could be round on this side. So our inputs again come on the left and the outputs go on the right, and this is our OR gate. And our output is P or Q, and it implements the logic function. So let's do some examples. All 4 of them, actually. So if I put 0 and 0 in for my inputs, I get 0 as an output. If I put 0, 1 in, I get 1 as an output. If I put 1, 0 in, I get 1 as my output. And again, if I put 1 and 1 in, I get 1 as my output. So this is the same operator we've been working with so far this semester. It's just that we're going to do it with pictures now. Now, when we're looking at a logic diagram, we're going to move from left to right always. So I might start putting more gates on here, and we're going to start reading from left to right. Why does that make sense? Well, the reason why it's the convention is because we read from left to right. But why does it make sense to go from the left to right since I put the inputs over here and the outputs over here?
Easier to connect the next gate to it.
Right. If I know that this output is here, then it may be the input to another gate. And so I need to follow from left to right because this might be the input to a new gate. And in order to know the output for a gate, I need to know what the input is. So I need to read from left to right to figure out what's the output of this gate because it's the input to another gate. Okay, so let's do an example of a slightly more complicated circuit with just one. We call a picture with some gates on it, we call it a circuit, a logic circuit. And it will implement a logic function. So let's just combine an AND and an OR. Say we have 3 variables, x, y, and z. Now let's figure out what the logic function for this is. We have an AND gate at the top that combines x and y. So what I do in order to figure out what the function is, after the output of the gate, I'm going to write what it outputs. So the very first gate gives me x and y. Now this output value is the same across this entire line. That's the convention, is that as soon as that output comes into this wire, that value goes into this gate. Okay, because these get implemented with wires. This is going to be a piece of metal wire. And so it will conduct electricity. We have a 0 when there's no current going through the wire, and we have a 1 when there's current going through. Okay, and we use it, that's digital. We use digital values, which are digits, 0 and 1. But any amount of current, measurable amount over a certain amount is going to be considered a 1. So this is considered to have the same value all along it. So the input to this gate is going to be x and y. This is an OR, so the first input is going to be x and y. And we're going to OR that with the second input, which is z. And that's our output function. Okay. Now, when you're doing this stuff and you get bigger and bigger pictures, these ands and ors looking really similar gets to be more confusing. So in general, in logic circuits, I'm actually going to draw this. When I put my output value, I'm going to just put times for and I won't write any operator for that, just the dot or not anything, and assume that that's like multiply. And I'm going to use plus for or. Remember that I said that and was like multiply and or is like plus. We're going to use that notation to make it easier to read our diagram here. So that will be xy plus z. And I don't put if I don't put the parentheses, I'm saying follow the regular order of operations, which is multiply. If I had a plus, I would need to put parentheses around it. Okay. So these are 2 equivalent ways of writing this, and you can write your diagrams any way you want in this class. I don't mind which way you write them. Doesn't make a difference to me. And then we also need to know how to do a not, right? Because we might have to put not x into a circuit, right? So the gate for not is called an inverter. And it's a not gate, and it just has one input and one output. So if I put x in, what am I going to get out?
Not X.
I'll get not x out. Traditionally in logic circuits, though, once I get more complicated circuits, I don't bother to draw the inverter most of the time. So instead of drawing the inverter, I'm just going to use this little bubble. We call this a bubble. Okay, so if I want to make a circuit for not x and y, that not only applies to the x since I didn't use parentheses, then I need to negate the x before it goes into the AND gate. So I'm going to put a little bubble on it. And this will give me not x and y. So let me show you the other thing in logic. For nots, we usually put bars over the variables. So another way to write this would be not x, y. So the bar only goes over the x because that's what gets negated. Are there questions about this? So an alternative way to write this gate would have been to take my x and put it through an inverter and then feed it into an AND gate and put the y, and I would get the same output. Okay? It doesn't matter to me which one you use. I like to do less work. So my choice is this one. Okay, we might also need to negate the output of a gate. So if this is an AND gate and that's a little inverter after the output, what's that output going to be?
Not X.
It's going to be not the quantity, xy. So be sure you put parentheses.
With
Yes.
the bar.
Sorry, if I use the bar, sorry, I combined my notations, which is also fine, as long as you're very clear about what happens. I put the bar over both variables because it also applies to the operator, which I didn't draw, but it's an AND. Okay, so it's really crucial, though, to pay attention to where these bars go. Okay, because, well, let me ask you, is this the same thing?
No.
No, because if I go and write this in logic, this is not x and not y, right? This is not the quantity x and y. And we know that an and has one 1, so negating it gives us 3 1s, right? And this is an and that just gives us 1 1. So we know these aren't the same. Right? So it's really important that these are not the same. Okay? Absolutely not the same. So be very careful with that. Now that makes it really fun to do De Morgan's, though. Because if I have something like this and I want to do De Morgan's, I have a fun little thing I like to do, and that is I think about sawing this bar on the top, like it's a board laying on my variables. And if I want to do De Morgan's, I saw it right over the operator. Okay, so I'm going to saw it. When I saw it, the operator changes from and to or to and, whichever one. And the bars that are left, you saw them, so they just fall down, right? So this changes to not x plus not y, which makes it really easy to do your De Morgan's when you're drawing these this way.
Can you give us the sound effect for that again, please?
No, it doesn't sound like sawing, but it was fun to do anyway. Okay, so if I had a plus and I was doing De Morgan's there, what happens if I saw through it?
Nothing.
That changes to a times, so I get not x times not y. So that's using De Morgan's for both of the operators. And why might I want to do that?
Simplification.
I might want to do that because I might need to simplify my circuit. Or I might need to change a circuit to all ANDs. If I have ANDs and ORs in my circuits and someone says, you only get to use AND gates, that's all we bought this year, and that's all you get to use, you're going to need to change every OR you ever generate into an AND. So you have to use De Morgan's for that, right? What if you have, say that you had an OR and your boss told you you couldn't use any ors. How do you change that into an and? I used De Morgan's, but I need to have a not to use De Morgan's, right? So how do I get nots legally? I can only get 2 at a time, right? I can get 2 at a time by doing double negation. So that was, if I had x plus y first, then I did double negation. When I do logic reduction, by the way, I'm only going to use the logical equivalence rules that are on your sheet. I can use any of those logical equivalence rules, but I can't use the implications because I want an equivalent circuit that gives me the same logic output. So I don't want to use the implications because they may not be the same. Okay? Equivalence is no matter what I can do, I can go backwards and forwards and it'll all be the same logic value. So then I can use one of the knots with De Morgan's and leave the other knot up there. So then if I saw through this, just the bottom one, I get not x times not y. So this is using De Morgan's on the previous line. And I have a cool picture to go with this that also helps you convert one to the other. So if we had x or a y and we knew we wanted to change it, basically De Morgan's rule tells me that if I have an or, it's equivalent to negating the inputs and the output of the gate, right? So what I do is I'm going to draw this really big. This is why this is fun, because you get to draw. Okay? And then I said an OR gate is equivalent to an AND gate with everything negated, inputs and outputs. So I'm going to draw my AND gate in the inside. It's just like, you know, you might look one way on the outside, but you're really something else on the inside. That's what this is like. And then we ignore the outside gate and connect up the inputs and outputs. And if I had an eraser, I would erase this. And so now I would get this equivalent circuit right here. Using De Morgan's. But I didn't even have to think about De Morgan's because I knew that ORs are secretly AND gates with knots all over the place. Okay? And if ORs are secretly AND gates, then ANDs are probably secretly OR gates, right? So that'll be the last thing we do, is to show you the super secret picture method for doing De Morgan's, is that ANDs are secretly OR gates. So an AND gate on the inside is really an OR gate with everything negated. So if I have x, y, that's logically equivalent to not x, ORed with not y, and then negate that output. And that's just a cool picture to help me convert. So if someone gives you a circuit and says convert it into all of a single gate, all you have to do is go draw the little secret intestines of all of, the insides of all of the little gates, and then erase the outer gates, and then you're done. And you didn't have to do any work. Okay? So that's part of what you're going to have to do on your homework. And the only thing that's on your homework that we haven't covered yet is working with these functions once we generate them from logic circuits, then reducing them. So that's the next thing that we'll be covering in class next time. Okay? Have a good night. Thank you.